Welcome to the design demonstration and learning video for Team 15, otherwise known as Hold My Juicebox Elon. We're sponsored by Bertrand US and Andrei Ryskov. Our advisors for this project were Dr. Turner and Clemson University. Here you can see our team members. Caleb was in charge of the regolith collection, Colin was in charge of the wheels, Adam was in charge of the drivetrain, and Blake was in charge of the electronics and controls.
In this video, we will discuss the project overview, project requirements, the design process, each subsystem of the design, the final design with failures and successes, and various learning activities. For the project overview, the team had to design a do-it-yourself kit for the 5th grade students of Mr. Holshoe's class. This vehicle or Mars rover should be capable of navigating an obstacle course and collecting regolith and depositing that regolith into a separate deposit bin. Design trade-offs must be considered to ensure that the constraints are followed and the customers are satisfied.
So this is the lunar rover track, where this is the landing pad where the lunar rover will start. The idea is to be able to traverse this whole area that's filled with all different types of sized rocks, while making it over to the mining area where you're supposed to mine for the regolith. Once you mine the regolith, you make your way back through the rocky terrain while also enduring the heat lamps. If you can make it all the way back to the beginning of the course, there's a small bin where you're supposed to deposit the regolith, which can be scored or be collected.
The Mars rover design was determined using design requirements that the team had justified. Some of the requirements included staying within a budget of $250 or less to make 2 rovers, create the vehicles so that they are under 450 grams in mass, make an easily accessible emergency stop button that stops the vehicle from moving. The vehicle must fit within the size dimensions of a 7-inch diameter hexagon, and the vehicle must be under 4.5 inches in height. And the vehicle should be able to collect regolith while also being controlled without touching it.
We started the design process with brainstorming sessions. Once we broke down the problem requirements, then we started coming up with ideas to fulfill these requirements. This resulted in the morphologic chart seen below. From this chart, the team will have 4 to the 6 possible solutions, resulting in 4,096 possible designs. Pew charts were used to score different subsystems based on a negative to plus scale for specific weighted categories. This scoring system is supported by engineering calculations. From the Pew chart, the team was able to narrow down the morphologic chart to designs A, B, and C. On the top of the screen, you can see our original design with the hemisphere collection, Bluetooth control, paddle wheels, 2-motor drivetrain, and triangular storage bin. We found out while prototyping that 3D printing hemisphere gears was extremely difficult. We had to switch to 2 square containers with 20-degree interior slope for the sand to fall out. We also had to eliminate the storage container so that we can mount our electronics and still meet the height requirements. On the bottom, you can see our finished prototype design without the electronics.
The drivetrain design of our rover features 2 centrally mounted motors with chain and sprockets so that each motor can transfer power to the 2 wheels on each side of the rover. There's a chassis made of aluminum U-channels to save cost and allow for it to be easier to manufacture. Each motor mounted in the center transfers torque and speed to a 3D print sprocket in the center of the chassis lengthwise, which then transfers torque and speed to a chain, which then transfers that torque and speed to the sprockets that are attached to each wheel, thereby rotating the wheels.
So we decided to go with a dual servo motor operated collection arm. The gears can open and close the collection scoops. The gear on the left-hand side rotates about the right-hand gear, which can open and close. And then in the back, a secondary servo motor will operate the elbow joint, and it can rotate 180 degrees.
The control subsystem was designed by inserting wires into a mini breadboard. This tool lets electricity flow to different locations on the board and allowed the rover to move. The electricity communicates with a small computing chip called an Arduino, and using computer code, you are able to tell the Arduino how the robot should respond whenever the buttons on a phone controller are pressed. So for the gamepad, the left side with the directional buttons control the motor directions, where up is forward, the right turns the wheels in the right direction, down goes backwards, and left spins the rover in the left direction. On the right side, you control the position and function of the collection arm, where circle and square open and close the collection claw, and triangle and X bring the claw up and down. And then we have a kill switch in the back of the rover that, when pressed, the rover would not be functional under any of these operations.
The wheels used in our rover were 3D printed so that we could test different tread designs. Different tread designs that were considered included paddle wheels for better leverage, digging wheels for better maneuverability, and alternating angle treads for better balance. In our final design, we used paddle wheels because the better leverage made it an ideal choice for climbing over obstacles such as different size rocks and different size obstructions.
Successes and failures for the project. Some of the successes were that the collection mechanism was able to collect sand and deposit it successfully if it were put in that position. The Bluetooth controls functioned, so we were able to connect a cell phone to the Arduino on the rover and control it wirelessly. Additionally, the battery pack that we had on the rover was able to last for a sufficient amount of time to power the motors and servos on the rover well. However, there were quite a few failures on the project. One was that poor motor mounting led to drivetrain unreliability, so the motors were able to rotate about the vertical axis of the rover. This would cause the motor sprocket to become misaligned with the chain, and the whole chain would sort of bind and not function properly. It wouldn't really move at all unless you twitch the controls to get it to work. The alignment of the chain and sprockets was not ideal and difficult to achieve in manufacturing. Ultimately, it was achieved. It was just very difficult, and a slight misalignment would still allow the system to function. Inconsistent controls, so it was very common for wires to come out of the breadboard or out of motors and stop the vehicle from working. But I think the main thing that a lot of these detail-oriented failures that could have been prevented or avoided would be if we had finished the rover in a better amount of time. So we would have had time to test, do slight redesigns, or come up with solutions on the fly to fix it, and then have more testing time. We didn't really do that. We didn't finish the rover in enough time, so we weren't able to address a lot of these small issues.
Gear ratios are used to change the speed and torque output of rotating components. In a pair of gears, the larger gear spins slower but has more torque relative to the smaller gear. The speed and torque ratios are equal to the ratio of the number of teeth between the gears. In the image pictured, gear B has 3 times as many teeth as gear A. Therefore, it rotates at a third of the speed, but with 3 times as much torque, or rotational force. The same phenomenon occurs between two sprockets that are linked by a chain. An example of this can be found on our Mars rover, where each side has 2 sprockets that are attached to the wheels that are linked to a sprocket on the motor. The sprocket on the motor has half the number of teeth as the sprockets on the wheels, and therefore rotates at twice the speed but has half the torque.